Okay, so hi everyone, I'm Flopin, and I will do an introduction about shadow coding with Bonzomatic, which is the software used during the Shadow Showdown. To begin with, I would like to say that English is not my native language, so if I might stutter or forgot words, I apologize in advance. So I see that some people bring their laptop if you want, and I encouraged you to download Bonzomatic if you have enough Wi-Fi and maybe type at the same time I'm explaining things. Maybe it will be easier to connect with what is going on by typing it yourself sometimes. But still, I will begin with something quite really the basics of what is that, why you are seeing red and green and black, and what is that. And on top of that, we will build some basic shapes in 2D, like circles or cube or lines, etc. It's totally improvised, so don't hesitate to maybe ask question at any time, and I will do my best to not talking too fast and explain it the better I can. So to begin with, what you are seeing here, the image, is what is called a fragment shader or a pixel shader. A shader basically is a program that will directly talk to your GPU, your graphic card, and whisper some dirty words to display the image. That's why it's real time, basically, and that's why it's quite fast. So the fragment shader is the last shader of the stack that is used to render real-time images. You have the vertex shader, the geometry shader, tessellation shader, and fragment. So fragment shader is completely 2D and happened after the rasterization. The rasterization is basically the steps where all your 3D points are projected onto a grid and became 2D points to display your 3D world in 2D space, basically. So this is just the fragment shader. So what we have here is just a plane with what is called the UV. If you are familiar with 3D stuff, maybe, if you already did 3D modeling on 3ds Max, Blender, Maya, things like that, a UV is basically the shapes being unfold. Like when you were in primary school and need to cut what is called a patron in France, the shape, the unfold cube. That's what is a UV in 3D. So here you have a plane, which is composed by two triangles, and the UV of the plane, so the unfold of the plane. And basically, a fragment shader is just having in the input the position of each pixels, and by using this position, you give each pixel a color. That's why you can see here red, green, and yellow. Why red, green, and yellow? Because red stands for the x-axis, so the horizontality. So here we have the value 0 on x, and here we have the value 1, not 1, 0.5, because Bonzomatic has this UV between minus 0.5 and 0.5. It's just what it is, but you can totally change it. But we will build on that base. Okay, so minus 0.5 right there, 0.5 right there. Same for the y-axis, minus 0.5, 0.5. That's why here you have red. It's the horizontality at the almost higher value. And this is yellow because it's a composed color of red and green, and that means that right there you have 0.5 on X and 0.5 on Y. Okay, why I'm talking about that? It's just because it's really important when you do shaders to know exactly in which space you are. Because as I said, as an input, you have the position of the pixels, and you need that position. You need to know that position in the fragment shader space to give it a color. And this, the green stands for the Y, okay? And the Z-axis, because you have access to 3 or maybe more dimension, the Z-axis is represented by blue. So here you have absolutely no blue in the image because I've set up the UV as the coordinate in X and Y and 0 on the Z. If I change this number by 1, for example, this is my, you can't see it well, but this is my, it means that in my fragment shader, you can imagine that as doing a step in front of you, out of screen, kind of, and that's why you have all blue mixing with still the red and the yellow. That's why here you have magenta color. It's because you have 1 in the z-axis and 0.5 in the x. So the two colors are merging, and same here for the z and the y-axis. Okay, and here if we were between, for example, 0 and 1, we will have white right there, which is not exactly the case here. Okay, so that's really the basics of what you have here. So that if you download Bontomatic, that's not what you have. You have a default shader, which is some kind of a tonal. But you can just erase all of that and just enter in the out color, which needs to be a vector 4, as it's specified right there, layout, location, etc. You can just specify you want to return in the main images UV11, for example. Sorry. Who in the room did not do coding at all? Okay. So just to be quick, I will not make a course about how to code, but just to be real quick, you have when you have a variable, you have to give it a type, and the type should match the value. That's why here the out color was declared as a vector 4. This is the type of the variable. This is its name. Okay, type of the variable is vector 4, and so you need to declare when you want to give it a value the same type. Okay. So vector 4 is some kind of an array of 4 value, is a vector of 4 value. You have vector 3, vector 2. Float stands for just a numerical value with, it's a float. And an int is the integer part, 1, 2, 3, etc. And the float might be 1.5, 1.2, etc. Okay. Maybe we can start by displaying some kind of circle to begin with. This is quite simple. So you have the UV right here. I will just put it at 0 again. 0 in z-axis. So you have the beautiful red and green colors. And just to display some kind of a circle, you can just do for example, float circle. Okay, this will be a distance. Okay, I will code a distance in that, and it's basically length of UV. you can do just that to begin with, and I will display that in the red color. Oops, it's not L, I don't know why I called it L. Circle 0. Okay. So why I have that to begin with? It's because I asked the length, so it's basically the same as it's called. It's the function, GLSL function, and it will give me the length of the UV vector. So when you are at 0, 0, the length of the vector is 0. When you are right there, the length of the vector is 1, for example, or 0.5 if you are between minus 0.5 and 0.5. So that's how you can display a circle to begin with, because you just want to have, what is a circle? Basically, it's just having the same points, okay? All the points are at the same length comparing to the origin of the circle. It's just the basics, the basics geometry, yeah, of a circle. Each point is as the exact same length as, comparing to the origin. So that's why doing just length of UV displaying a circle. Okay, but it's not really, it's kind of blended, okay, because the value here are just root length of UV. So that's why you have a nice dégradé blend. If you want to draw a clean circle, you need another function which is called step. Step is just a threshold, and when you are above the threshold, the function will return 0, and when you are after the threshold, the function will return 1. Okay, so it's just 0 or 1. It's like having a Boolean function, true or false, with a threshold. So for example, if I want my circle to be, I don't know, with a length of 0.2, I can do a length of 0.5 because it will take all the screen now. Remember, we are in between minus 0.5 and 0.5, so I need to take something smaller. So if you want to display a circle with maybe a length of 0.2, I can use the step function and give it a threshold and what I want to threshold. Okay? And so I have a clean circle. Oh, shoot, I'm sorry. Excuse me. Okay, let's take it. Shoot. Maybe behind, I don't know. I'm such a... yeah. Maybe because it's... yes. Okay, thank you. Yeah. But you can see, for example, that I have, as it's a tough cut, the step function is really like, you can imagine a stairs. And it's just like, if I am out of the threshold, I am directly returning 1 or 0. So you see that I have some kind of aliasing right there, some kind of stairs effect. And if I want something more smooth, there is a function, another, called smooth step, which is, we can help with anti-aliasing. A little bit, not quite well, but... And smooth step took 2 value as a threshold, and it will blend between the 2 value, and then under the first value, it will be equal to 0, and above the second value, it will still be equal to 1. But between those two, there will be a nice blend. So for example, I can put that, and you see that I have a smoother edge. Okay, so it's kind of the in-between with what I had before and what I had after the step function. So I can turn out that shapes into black and white, maybe, to be cleaner or prettier. So basically what I can do is just, I will code a vec3 value, which I can name color, my final color. And I want in the free value of the vector free, which can be represented as red, green, blue, I want the same value in those three to have black or white. So what I can do is just declaring another vec3 and call it call vec3 of circle. So it will just automatically put me the value circle in the red, the green, and the blue. So I will have something prettier with that. So I will have, it's more white, black and white. Just a quick precision. Doing that, putting one value in three, in the array of three, that is given by the vector free. It's called swizzling, and it's not possible in HLSL. Here we are doing the coding language is GLSL, and you have another one. You have lots of metal, Vulkan, etc. But this one is GLSL, and when you are using HLSL, you can't do that. You can't do swizzling. It's not working. In HLSL, you need to specify circle, 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 which here gives me the same result, but will work in HLSL. Okay, so now maybe we can twist this circle a little bit, or maybe, no, we will display a line. So what is the line, basically? For example, if you want an horizontal line, okay, might be represented by the fact that the UV have an X coordinate and a Y coordinate. Okay, so maybe what you can do, if you want to display an horizontal line, vertical, you can just say to the pixel, the pixel position in those lines, that they need to, in this direction, thank you, in this axis direction, you want to take all the pixels in a range of, I don't know, maybe 0.2 on UV point X. No, on this axis, you want to take a range of all the pixels on this axis between minus 0.2 and 0.2, for example, and it will give you a line. So how you can write that? So float line, it's still a float. We can start with absolute value of UV point X, for example, and see what it's done, what it did. Okay, so what ABS stands for absolute value, and in those kind of in the fragment shader, it will give you a symmetry, because, for example, minus 0.2 become minus 0.2. Okay, every pixel with a negative position are bring back to the positive position, because it's an absolute value in mathematics. So you have a symmetry. So right here, what I did, it's just creating the symmetry along the UV x-axis. Okay. So now I can do exactly the same as the circle. For example, if I want my line to be between minus 0.2 and 0.2, I can do exactly the same. And I will have something less blended. Like that, for example, exactly the same. And here we have our line. Maybe I can make something less smooth and maybe less wide. Okay, just change. Now you can just change those value to switch between bigger or smaller line. If I'm doing the same, I will just call it line X. I can do exactly the same on the y-axis to have an horizontal line. Basically, I can just copy-paste this line and change that by UV point Y and maybe change also the name because it will give me an error if I don't change the name. And I have exactly the same, but in the horizontality. Now, if we want, we can twist this line to display a sine wave. Okay, so if you want to represent yourself how it is to bend the line to display a sine wave, you can represent it yourself by saying that it's just dragging those pixels up, okay, along a sine wave on the x-axis. Okay, if I want to do this movement, it's just dragging the pixel up by a sinus on the x-axis. Okay, so I can do UV point Y. That's my pixels in the y-axis. I want to drag them, so I want to pull them, which is represented by an addition to it. In the fragment shader, plus is translate something and multiply is scale something up, okay? And the same, minus is still translate, but on the other side, and divided is scaling down. And I can do just UV point Y plus equal my sinus along UV point X. Okay, and why I have that? It's because my the face of the sinus is not, it's too wide. So I can just multiply my UV point X to make more of them. And maybe also what I can do is just still pulling my pixels, but maybe less, a little bit less. So I will diminish, reduced, yes, diminish or reduce the effect of the sinus on the UV point X coordinate. And still my phase is too, okay, so here we are. Okay, so I just pull out the pixels with a sinus wave. And again, if I want, I can display, I can make a smaller, oh, sorry. I can make a small, that's why, small line, etc., etc. I can do the same with the X line. And this will be a little bit different. It's just the over axis. Okay, here I pull out the Y coordinate of the pixel. Now I want to pull the x coordinate through along the y, the sinus on the y-axis. It's the same thing, but you just switch the two coordinates. We want x plus equals sinus of uv point y. We just write exactly the same thing. Oops. It's because my y is also being bended. And so I I did the two effects at the same time. Okay, so that's for the how you can bend or pull your pixel and display things with it. And the same can apply to the circle. If I just drag this line, those two lines maybe, here, apply the two of them, and then use the new UV I have, because when I call this UV right there, it becomes the modified UV I declare here, okay? And I call the circle, I will have the two effects at the same time on the circle. So it's doing that. If I, for example, that, to see better, in any time you can add the time to your shader and it will animate along the sinus wave, for example. So if I do float time equal f global time, I'm just declaring a variable called time because f global time is a pain to type. It's really long. But it's something you have directly in Bonzomatic by this uniform here. It's declared right there. So it's the time in seconds. And for example, if I had the time here, you can see that my circle is bouncing. And I can do the same on the UV point X. Plus time. So I have a wobbly circle. If I keep up with the multiplying by 10, it's just and you can easily get interesting effect just by animated your function. Okay, maybe it's a bit boring because we just have one element on our image. Maybe we can duplicate it in the 2D space. To do that, I just need to shrink my sphere a little bit. So let me just. Okay. So it's doing super bizarre thing now. It's kind of interesting. Maybe I can keep it for another shade. So yeah, now I have this little dot, and I will just get rid of that for the moment. For the movement. So now if I want to duplicate this little dot, we used a function called modulo, as it will give you it's the real mathematical modulo which gives you the rest of the integer division. And in those cases, it can help you duplicate the space. So for example, if I am doing before calling the UV into the circle function, I can do UV equal modulo of UV, a period, for example, 2. No, it will be too far. 1.3, okay? And I duplicate my dot. But you can see that I create, basically I create new square of UV. It's like cutting down your UV. But I did not put the dot in the center of the cutting UV. So that's why you have a quarter of a dot. To do that, you just have to do minus the period divided by 2. So, or multiply by 0.5, it's the same. And I just put my dot in the center of each square I created with the modulo. Okay. And now I have an infinite space filled with little dots. So if I am doing, for example, UV plus equal time, so I'm just basically translating all my UV set with the time, you can see that I have, maybe it's too fast. Let's take it slowly. And I have an infinite space of spheres. Okay. Maybe now what I can do is, I don't know. You can do exactly the same thing for the line. For example, we just get rid of the time to begin with. Okay. For example, if I am using my line X, which is more than line Y, I should call it line Y, but it's the vertical one, line X. So I want to, this function, line X, give me the horizontal, vertical, oh gosh, I'm so bad at that. Vertical line, but it's infinitely vertical, okay? So what I just need to do is duplicate it along the x-axis of the UV because it's already infinitely vertical. So if I am using my line X right here in the color, and as I did not change my UV, you can already see what it's done, but I can just do UV point X and it will give me exactly the same thing. And I can still use my time to translate my space, and I have an infinite space of lines, vertical lines. Exactly the same for the horizontal one. And I can also still apply my sinus to it. But I have this weird effect because it's the same problem as I had before with repeating the space with the modulo without putting the dot in the center of the new space I created. It's because I'm doing a sinus movement inside those new those new square of UV, and it is cut down. So what I want to show you with that is that the order of your operation has a huge importance right there, okay? If I don't want my sinus movement to be cut by the new UV I did with this line, I just need to drag that on top of the duplication, okay? Because when the program is running, yeah. It will do the operation from the bottom. The code is read from the from the top, but from top to the bottom. But the mathematical operation appears more from the bottom to the top. So this is why I have this cut line. It's because I'm doing mathematically the sinus before duplicate. And if I'm doing the sinus after duplicate, which encodes is translating by just putting the line above it. You see that my lines are not cut anymore. Okay. So the stack of your operation has a huge importance. Okay, if you are using multiple effects and multiple space bending stuff in the same function, you have to be sure about the order. Is that okay? Okay. So that's Evil.
Hi guys, I'm gonna help you guys with it.
But nobody bring his laptop, so better.
Okay.
No.
Okay, I'll just chill for now. Keep doing your thing.
Maybe you can help me with English sometimes.
Sure. Just take a seat now.
Um, is that okay for 2D stuff? Just do you have any question? Yes. No. Okay. It was just a bottle up. Okay. No. Oh. Don't hesitate to talk with me later if you have more questions. So, no? Yeah. Okay. A little bit. Okay.
Tu veux t'asseoir?
Non, c'est bon, c'est bon. C'est gentil. Know what we can do. I don't know. Maybe 3D? Do you have time for 3D? Do you want to learn about remarching? How to do 3D when you are in the 2D? Yeah, okay. So let's do 3D.
Shading's boring, bro. Let's get 3D going.
2D shaders can be quite well,
Yeah,
please.
what you did yesterday was fucking cool in
Thank
2D.
Okay, let's go for 3D. So basically, a remarcher, this is the technique we used mostly to display 3D onto a 2D canvas, which is basically what is a fragment shader. So the technique is called remarching, and often, as a shader showdown runner-up, we used a specific technique of the remarching, which is an optimization of it, which is called the sphere tracing. I think it was brought by Cube in his thesis.
I think so.
And what is sphere tracing? Basically every renderer system in 3D shoot array. It's the basics of every renderer. Okay, so you shoot array. In this case, what sphere tracing do is shooting array for every pixel, okay, and you have to march along the array, which is why it is called the remarching. And the optimization of the sphere tracing is using the distance from the nearest object to do your step. Okay, remarching is basically doing fixed step along an array, like you enter step 1, step 2, step 3, etc., and colliding with stuff. Yes, I am the camera.
This is a camera origin, and she's marching along it.
Like that. Okay. And sphere tracing is, for example, if I have a bottle right there, it's my nearest object. So I will march until I will do a step, a really long step.
Straight to the object.
Straight to the object.
Straight to the object.
Like that. So you can see I did less step, etc. And I am really close to the object. So I'm doing small step, and then the next object, comparing to, so it's a sphere tracing, so it's in 3D. Imagine it's the ray of a sphere, so it's in 3D. And then I can décoller.
I think, yeah, so you just keep going and until you hit the next object, and then again you trace. But I'd like to make the allegory, sorry, for me, from that angle, because,
Yeah.
so I'll just, for 1 minute, try and make a metaphor, sort of, even trying to put it in a 3D space context. What's going on here is that we've got a 2D plane, but we are representing a 3D scene. And I just like to take this position because we are looking at what we call a view frustrum, which essentially is when you have a 3D camera, and this is also true not just in real-time 3D, but in 3D packages, 3ds Max, Cinema 4D, you always have a camera. But in the end, guys, even though we do 3D, everything goes back to a screen, so it becomes 2D, right? So these cameras, and that's why they have those gizmos in things like Cinema 4D, whatever, 3ds Max. You have a camera, you can see, you can see the cone and the gizmo of the camera, right? And how it ends at a certain point, and that's the view frustum. That's the 2D plane that you see it through. You should see this as a window. It's like you looking out a window into a 3D world, right? That's what a 3D camera really is. And what we're doing in ray marching and what Flopin just explained just starts from the camera. I just wanted to step here to so that you guys understand about the 3D space of it, which means that we are now at the, let's say, at the origin of the camera, right? And I'm basically shooting a ray every frame. I'll just add to what Flopin said, which is totally correct, which is we're shooting rays once for every pixel. I'll just like to add for every frame, just so you guys understand the staggering sort of amount of calculations that we're actually doing, which is why you need a good GPU to do ray marching and to do this 3D stuff. That's because for every frame, we shoot not just one ray per pixel, well, we do, but we march it forward as Flopin just demonstrated. So for every pixel, this is the camera origin, right? Let's just say if we had a 3D scene, this is our window, we're looking through it, we're gonna put some spheres, we're gonna put some shapes in it. And I'm just the ray here, like she was a minute ago. And I will start by going, this isn't exactly correct, so don't quote me on this, but I'm trying to make it accessible to your mind to picture it, because these things are very abstract and sometimes it's hard to actually picture the actual thing, you know? But what I'm doing really is, if I'm here at the camera, I will shoot a ray from here through the frustum. It means that I'm shooting a ray here. Am I right here, sorry, or am I not?
Yeah.
Sorry, do you see where I'm going?
Yeah.
You shoot through the frustum and then you march forward through the window. If I'm making a simple allegory, you go through the window and you march forward, as she just explained, and you will make a big step forward to hit your object. Then you draw it. Yeah, you did it very well.
Do it.
I do it. Not bad. And then we land at the object, and then we draw it, and then we keep going. And basically, we do this until we've hit geometry, and then we stop and we color it, right?
Yes.
So the idea is that your rays go, and let's say we have a sphere here, I'm a ray, I just go forward until I have hit some geometry, or, so I'm trying to simplify a bit as well, sphere tracing. What I'm trying to say is that essentially we're just moving a ray forward until we hit an object. And if you hit an object, you will color it according to what you have set up in your lighting and everything, and according to the object. But if you don't hit an object, you just keep going forward until you've reached
The maximum step.
The maximum step. Or the far plane. You can also have a far plane. I'm sure a lot of you do 3D and know about this as well. In 3D, for any camera, you can say a certain limit at which the actual scene stops being rendered to optimize it, especially in real time. It makes a lot of sense, obviously. And in ray marching, you can also have a far plane. So you can shoot your rays and go, right, we keep going until you get geometry, or you've reached so far that it's just too far. And then you'd usually have a fog effect so that, that goes with
Yeah,
that.
I will type it later.
Anyway.
Thank you for this intervention. And what is really beautiful, I think, with I don't know where the just don't Larsen effect. Don't know. What is beautiful with remarching and sphere tracing, etc., is that the question you might ask yourself is, but I don't have geometry in the scene, how can I do? And that's the beauty of it. Geometry, you will construct it with mathematical function, which will give you a huge range of possibilities. I think myself as being infinite, because you can basically use every kind of mathematical function you can think of. And that's why, for a little bit historic tips, that's why remarching was conceived in the first place by John C. Hart to represent Mandelbrot set in 3D, called today Mandel bulb. So remarching was invented just to display fractals in real time.
And in 3D.
And in 3D, yeah, fractal in real time and 3D. So to begin with, for example, we will see the function of the sphere. So it's the same for 2D, but for 3D. So sphere, so float sphere. It's still a sphere because we are talking about distance. Okay. What I will need for a sphere is a basic position, which I will call vec 3p, because we are doing 3D now. Okay. So I need 3D. Oops. I launched the loop. Okay. And what are the same the same property? Yeah. Well, what is the same? No problem. What is the same property each point of a sphere share?
Oh, she's onto something. I've never had this explained to me like that. This is good.
So each point onto a sphere is at the exact same length from the origin of the sphere. Okay, that's the definition of a sphere mathematically. Each point of the sphere are at the same length to the origin of the sphere. So that's exactly what we will wrote in this function. That's the same. So as we saw before, when we draw a circle, we did length of UV to have the distance from the origin. This is the same here. P is the origin of my sphere. Okay, so what I need to do is just returning the distance from the origin of the sphere minus a value which will be my radius. Okay, and that's it. And that's the remarching function for a sphere. It's just a distance. And what you need to represent is just what is the property, the common property of each point of a sphere in the spectrum of distance. Okay? So that's it.
Yeah, I was just going to add that I'm going to make another allegory, I guess, metaphor into the 3D world as well. And again, a lot of you, I'm sure, know about 3D models and things like that. Just to compare it. When you're in a 3D package, like C4D, whatever, Houdini, when you make a sphere, it's not actually a sphere, bro. It's a bunch of points connected to look like a sphere. I'm not dissing it. I understand it. I'm just saying, when you make a 3D sphere in 3ds Max, you make a bunch of points that are looking like a group, in a group look like a sphere. Then you make faces, you get a UV map, blah blah blah. That's how you do a sphere. We make shapes, primitives, from the math equation of it. That's the difference. But really, in the end, it's the same visually. Do you know what I'm saying? You make a sphere in 3ds Max, you make a sphere in ray marching, it looks like a sphere. That's the main output product you want, right? And so what I'm trying to say is that these primitive functions that Flopin's explaining now, you can call them in your code. When you call them in your code, you should see it like, I'm in 3ds Max and I want to create a sphere and I'm going to move it on the right and I'm going to create another sphere, move it on the right, and then I'm going to create a box and then move it there. And you know how you would model. Let's not talk about pushing faces for modeling. I'm just saying about 3D compositing and actually laying them out. We actually do the same thing. Now that you have this sphere function, she's obviously going to explain now how to use it in your code to call it. But when you call it, you create one, you know, at a certain position. It's the same thing as you creating something in 3ds Max. So all I'm saying is, if you're thinking, whoa, this is all like math stuff, it's so next level, and fuck it, I don't really, you know, oh, fuck math and all this. Well, math is sexy because ray marching will show you this, but you know, don't get too bogged down to it. Don't get too worried about if you don't understand exactly how the sphere function works. Like, this was a great way of explaining it, about how it's all its points are the same length from the radius. It's brilliant. I never heard it, by the way. It makes total sense. Thank you very much for enlightening me.
You're welcome.
But what I'm trying to say to you as well is, don't worry too much if you're overwhelmed by all this. You're just gonna get this function, and then it's how you use it. And these functions are available on some webpage. I'm sure Flopin's going to mention it now.
Yeah,
anyway.
we all started by copy-paste.
Yeah, that's right.
Over code.
That's right.
Mostly Inigo Quiliv.
Yeah. But, and just to finish, what I'm trying to say is that what we are building here when we do a ray marcher here is a little 3D package, right? Which runs in real time. You should see it like this. We're building a little C4D here. We're going to do the lighting. We're going to do everything that C4D does. You know, obviously not to that crazy extent and stuff, but it's the same. And so what we're doing now is creating a sphere function, and it's like having a tool
Toolbox.
in your toolbox with a new icon, and it's a fucking sphere, and if you click it, it creates a fucking sphere. That's exactly what this is, in a nutshell. Thanks. Sorry.
Thanks. No problem. You're here for that too. So now I need to use the sphere, as you said. So that's where you will write the remarching loop, because you are shooting array and you need to do steps on it, and it is done by a loop, by coding a loop. So I will just get rid of all of that and just keep the color. So I need a ray.
What is going on next door, bro?
So I need a ray origin, which is the position of the camera, as we pictured it sometimes ago.
Arrow is ray origin in our case, which really means camera position.
Camera. Oh, yeah, I can call it as I want.
Yeah, just stick to arrow. I think is good, because although you can change, you can name your variable whatever you want. If you go on like Shader Toy and you want to get into this, I mean, obviously the place is to go on Shader Toy and see all these 3D ray marching shaders. Most people have these slight conventions, like arrow is ray origin. You're going to see that all over Shader Toy. So I think Flopin is right to call it arrow.
Oh, okay.
Oh shit, you changed it.
No,
oh,
I
shit.
can call it arrow.
I think just for the sake of you take this workshop, then you go home, you go on Shader Toy, and you're not totally confused, like, what is this, what is that? We're going to try and stick to maybe Shader Toy convention, RO,
Yes.
RD.
Okay.
Yeah,
Okay.
maybe. I don't know, I mean.
No, you're right. And I want to put the simplest way, in my opinion, is to put all the objects at the origin and being a little bit behind the origin. So for that, The Z, the Z value, which is the third in the vex3, would be, for example, -3. And so it's like being three, not steps, but three value on the Z-axis behind. Okay?
It's like the center of the scene, let's say, would be where the screen is, and we're stepping back a bit so we can
Yeah.
look at the screen. You know, otherwise you're like straight at the screen, basically.
And you can't see anything.
And it allows you not to have to move every single time you create an object. Oh, I've got to move it 30 bit further because my camera is at 0, 0. In fact, it's the same, I guess. Again, if you're in a 3D package, you create spheres. They usually tend to drop at 0, 0, and the usual sort of a roving camera is always back.
I just need to code a position. This will be the position will march along, and to begin with, we are at the camera position, which is the ray origin. Okay. And then I need to do a direction. In which direction I will march? There, I don't know. So I need to code it.
Yeah, so RD is basically ray direction, which really stands for the camera direction. So, not want to get too mathy with you guys right here, but it's a directional vector. Essentially, you should see it as it's a target camera. See it as that, yeah? You've got a camera, the position is 0, 0, 0. Well, sorry, in our case, a little bit back, -3. But then you could say, well, I want the camera to point forward, in which case your direction should be 0, 0, 1 because it's pointing forward. But if you want it on the side, then you'd use. Oh yeah, sorry, we're not going to do the whole.
No, I think we get camera. It's too cool.
Orthographic camera.
Yeah, basically.
Yeah. Sorry, not orthographic, but we're going to do just a very simple sort of camera that looks forward. But still, you have to have a direction which is to look forward, because you could be looking backward, you could be looking on the left, you could be looking on the right, whatever. You know.
And if I am behind something and looking backward, I can't see things. So you need to, but you can totally swipe those two. I mean, you can be in front of something and looking backward. And if your object is there, it's the same thing, okay? I can do 0, 0, 3, and here looking -1. It's the same, basically. It's just in which direction you want to point.
But also here, sorry, I'll add that the ray direction we've got here is derived from the UVs. So as Flopins explained before, this builds a map. You should see it as a coordinate systems for the pixels, right? So let's just say this is 0, 0, and then if you move to the next pixel, 0, 1, you know, they're actually tiny little numbers like 0.000001, but whatever. What I'm trying to say is that you should just see it as when you're at school and you had an XY graph, you know, and your math teacher was like, plot the points at X, 4, and 5, right? So that's like a UV map. That grid that you have is like this UV map. So our direction for the camera, we are like moving forward. We're saying move it forward, but through the UVs. And this is where I was trying to do the image before of like we're shooting rays from the camera through a view frustum, because we know this is pixel 0, 0, right? So we go, fuck it, shoot a ray through pixel 0, 0, and that's the direction of our camera. And we're shooting rays like that. I once made an image on my Twitch stream about when you ray march, you should see it as you've got a gun, it's like a pixel gun, yeah? And you will only see the scene if you shoot a laser ray with your gun, shoot straight, if it hits something, it will color it. So now move a little bit, shoot again, color it. Move a little bit, shoot again, color it. And if you was to do that in real life, and if you were to shoot paint bullets to discover the color, it's actually, I believe, what your eye does, really. That's how you would get the scene in ray marching. Do you know what I mean? You got a pixel gun, and every time you shoot a bullet, you see the result. And then we move a tiny bit, like a turret, up and down, and we're literally drawing each pixel like that every frame. But sorry, I just wanted to jump in for the camera direction,
Yeah.
which is influenced by the UV map, which is the pixel coordinates, really.
It's basically drawing the frustum of your camera in the 3D scene.
That's right.
Blender 3ds Max. The frustum is like the kind of weird tetrahedra you have on the display of
the camera frustum is that sort of code you get
Yeah.
from a virtual camera. And what we talk about when we talk about the view frustum, it's usually that plane, that 2D plane, right, that the camera sees. As we say, the window, here's the window.
Okay, that's it. Thank you.
No worries.
I will just code a basic float value that will help me color what I have in the scene. And now move on to the famous remarching loop. So it's a for loop. You can do a loop of a float or int. I think it's not very well. So I choose a float
interesting.
function. Then I need to put a stop to my function, to my loop. So for example, 100. I will step 100 times if I don't hit something. We'll see that later. And marching along my the array is representing by just incrementing the iterator in the loop.
But sorry, does this already work as a far plane as well?
Kind of.
Kind of, right?
Yeah.
It's not like
It's not totally like saying that you have to stop the loop for
that's
loop
right.
if you are too far. It's not
Yeah.
exactly the same as a for plane, I
that's
think.
right. That's right.
Because right there you will still get to the 100 steps if you're not hitting things.
That's right.
What you call the for plane is more like if I
break,
am.
you break.
You
if
break
you're far.
if you're too
We'll
far.
we'll see about it. Let's just. She's gonna type the code and then we'll see even about the quick far plane. What I mean, it's very easy actually to understand.
Yeah.
It's also to optimize because sometimes you know that you've got some. Usually you would have like fog, for example. If you have fog, you know things have disappeared already, and you're like, okay, well I'm gonna stop all those rays from overshooting past the fog, essentially, and then you just stop the operation of pushing the ray forward and you move to the next pixel quicker. So you might think, oh, that's cool, but whatever. But actually, if you do that on 50% of the pixel, it's so optimized. It really makes everything so much faster.
So I need to code the distance in my remarching. So it's basically coding the environment. It's the geometry. Okay, it's the map. Can call it a map or SDF for sign distance function, etc., etc. It has a lot of names, but now it's just look at it as being your 3D environment. This float D, okay, represented by a distance, but it's your 3D environment.
And again, on Shader Toy, you will see it usually as being called D or DF because, you'll see, it's the result, it's the distance field, which is just basically just see it as your scene, yeah.
And as you have your field, yes? Yeah. Like that? Okay, cool. I can do more, I'm sorry, but maybe I can add a blank line. Yes, you want to be... Okay, I can add blank line, so...
Sorry, good point, guys.
Like that? With the...
more, and then you can push it right to the top, I guess.
Yeah.
I mean,
Like that, maybe, so you have the sphere and you have the main.
yeah.
Okay, it's good? Cool. And then this is where I need to put a condition in which I will stop the ray. So as we said, we stop to march along the way when we hit something. So hitting something, when you are talking about distance, it's just basically having the distance being less than a really tiny value.
Yes, your float D basically will give you a distance. So just gonna when we shoot the ray, we know the ray position. Okay, you should see that when you make a ray marching scene, you make a mega math function, okay, which defines your whole scene.
But don't be afraid.
Yeah, don't be afraid. But what's funny about it is it's simple when you think about that it's a math equation that will give you 3D graphics if you give it a position. Look, it's more complicated, but let's simplify it for a minute. So if I tell you, hey bro, I'm at 1, 5, 10, right? So 1 on the x-axis, 5 on the y, and 10 on the z. If I run this position through our mega function that defines all our scene, we're just seeing about having just a sphere at the moment. Obviously, you're going to want to add more spheres or whatever. We'll show you how to combine like sphere function calls and stuff. That's cool.
If we have time.
But in the end, you are still getting a mega function, math function, which only takes one input. That's where it's simple. It only takes. Don't worry about the bloody function itself. It doesn't matter. What matters is that you need to understand it takes as an input the position P, which is the ray position at the time where it is at the moment. But this returns a very simple number, which is the distance you are at from the geometry. So, sorry, this is just to sort of simplify and clarify this D thing. And as Floppin just said, the result is D, right? That's the result of our function call, our mega function call. Well, it's simple. If the number is less than, let's say, 0.001, that's the distance to the geometry. That means we're fucking close. That means we're like here, right? So draw it. And yeah, sorry, go on, yeah?
This is okay.
Yeah, good point. That's the radius.
That's the radius. I think I will use paint in this to draw something. So don't be too harsh because I will use my mouse, but I think I will use some paint, and you will see my drawing skills and understand why I'm doing shaders. Because that's awful. So, what is a sphere? A sphere is that, basically, you have the origin, okay? And let's say, for example, that you march along the ray and you are here, okay? You are here. So you are outside the sphere, etc. So what I'm doing by doing length of P is doing that. This is length of P. That's awful. This is doing length of P.
That's right.
And then I need to go back.
This is the radius. Yeah.
And I need to go back
By
from the
-1.
value of the radius to have this point and this point and this point and this point and this point, etc. So that's why -1. So it's minus the radius.
The radius.
I'm moving like that, and what I really need is not the center of the sphere. It's points.
Yeah, because we're not drawing the center of the sphere. We're drawing, of course, the outside. And when we're on the surface of the outside, we stop, right? And that's where we want to be. Obviously, we don't want to be inside. But I'm just going to, literally add, just for you, I guess that might clarify it a bit as well. You can do, see it like this, really. Yeah. And then we add another variable here, a float, which is just the radius. You could also obviously do this. That's up to you when you draw your spheres. In our example that Floppin was doing, we just wanted a sphere that was 1 unit of radius wide. But of course, if you were to do your own Raymark chart, you want to create spheres of different sizes, I would advise then you do your sphere function like this, for example. If all your spheres are the same size, then, remove the variable and hard code the radius. But yeah, that's exactly what it is. The -1 was really the radius of the sphere.
And now, as I set it as a parameter of the function, I just need to bring it back right there when I call the function.
Sorry, didn't mean to break your code.
No problem. You want me to fail? So, we are shooting array, we are doing the for loop, we are setting our distance to be the 3D environment, And here we are setting the condition. Understand that just being we are closed to something. Okay, this is what it means. We are closed to something, and what we can do when we are close to something is that we say we stop marching. So break the loop. Okay, and what I will add to just to just see my 3D environment is my function, my value shade here, which is shading. I can call it shading,
maybe.
because not minifying the code right there.
Yeah, that's right.
So shading, shading equal the iteration I'm in divided by the total number of iteration I will do. But don't worry about that. It's just for displaying a kind of
shade.
first shading.
This is a classic, and I mean classic flopping trick. This is great. I learned this from flopping, guys. And it's really great. It's like very simple way of displaying a 3D geometry by shading it according to the distance.
Yeah.
So basically,
Z buffer. Yeah.
that's right.
That's right.
That's right. But I'm saying, for example, before seeing this trick, I'll be calculating a diffuse shading with dot product and all this stuff.
Also.
Yeah, of course.
And then said, oh yeah, the depth value. Yeah.
Yeah. Yeah, exactly. So obviously, as this is a workshop, it's really great that she's showing you this because it's so much simpler than calculating proper lighting like in C4D.
Yeah.
But I can show you this next as well. But this is a great starting point and a great trick. I love it. Thank you.
You're welcome. And just to be more precise on the color we will add to the shapes or to the background, I will code a boolean, which is called it, which is false for now, and I will just set it as true when we hit something. Okay, and that will help me coloring what I hit and the background, which is basically white, the space where I didn't hit anything. Okay, and now I just have to do one more thing, and you absolutely can't avoid it. Because I say that because I do it a lot. When I started remarching, I was forgetting about marching along the way, because here we set up our for loop, we set up our distance, we set up our condition where we stop, but for now we don't march along the way. We do nothing. And to march along the way, you just have to
You need to push it forward every iteration in the loop, basically.
So you need to, the P is your position along the ray. You need to add to the P your distance. That's why we are using the sphere tracing. This is basically sphere tracing. Okay? Because
that's the big step.
Yeah.
We don't just step a little bit. Sorry, just jumping in. You can also do a different type of ray marching where you just step a little bit forward, let's say by 0.1 or whatever, and you step by it's called a fixed step, right? Where you just keep, and in some cases, by the way, that's exactly what you want. If you do, for example, clouds and stuff like that, it would make sense to do that. Obviously, it's so much more optimized if you step forward by the whole distance of the object because you know where it is and you step forward. That's the sphere tracing bit of ray marching, essentially.
Yeah, the optimization is right here. It's putting the distance here instead of a fixed step. Okay? Thank you. And so D multiply by the ray direction, because we still need to march along a certain direction.
Yeah.
So you need to bring back the ray direction right there. Yeah, sorry. Okay. Sorry. So yeah, you need to bring back the ray direction to be able to know where you need to march. Is it there? Is it there? Is it there? Etc. Yeah.
Cool. And sorry, just to clarify as well, because some of you still might be, this is big enough stuff, but, that's why you're here. This is a for loop. And, for those of you who are not like huge coders, it means that basically it just repeats the operation for a certain amount of times. And in our case, we chose 100, because that's how much is the maximum amount of steps, in our array marching, so that it doesn't just crash the computer from infinitely shooting array forward and just not moving to the next pixel. We need it to stop. So this bunch of code, sorry, this may be very obvious to some of you, but I just wanted to clarify for those that are not that, versed with coding. This code runs once per pixel. This function runs once per pixel. And it goes like this. It does this line, 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 this line. And here, it goes, cool. This block, it's going to get repeated. So it does this line, this line, this line, this line. And as long as this... Oh, no, sorry. Very bad. That was a very bad example. Sorry. It does this line, and then it checks this. And this says, if the distance is less than 001. So at the beginning, obviously it's not, because you're at the camera. So it goes, nah, that's wrong. So it goes straight to here, but then it's got a loop here. So it goes back up to here and does this 100 times. When the condition here is met, this code... So when we eventually hit some geometry, this code goes, hey, is this less than 001? It goes, yeah, you've hit the sphere, basically, so we're going to color it. I'm just saying that what we do now here is like, we do some shading, we draw the pixel, and this break, just to clarify, this breaks the loop, basically, because otherwise you could do the shading and keep going. For some reasons, for example, if you want transparency, you gotta color it and like accumulate it, sort of thing. So this is an advanced example, but that's why in our simple example we break. We don't have transparency, we don't have nothing fancy. If we hit the sphere, we color it. So we break because the current ray that we shot for the current pixel has now reached its destination. So fuck it, let's break. So this makes sense?
Yes, yes. And this is where you can see it's really a huge amount of calculation because we are shooting array for x pixel, and in this way we are doing 100 iterations. So it's 100 iterations per pixel.
Yes.
Okay.
Yes, it's staggering. And per frame. So, when you run your...
Pixel.
Can you imagine... So when people talk about optimizing shaders, they got a fucking point. Because if you run this operation 60 frames a second, I calculated this, something around 1920 by 1080 is roughly 220,000 pixels. So this thing here runs, let's sort of calculate it quickly, 100 times per 220, so you've got like 22 million times this function runs per pixel. It doesn't make sense. I don't even know. It sounds so staggering.
No, per frame, not per pixel.
Frame, sorry. Yeah, per frame. But that's one frame. So per second, this runs 60 times 22 million times. It's nuts, bro. So when people say, oh, you remove this line of code, it will make a difference. Everything makes a difference almost,
Yes.
I mean, every operation that we put within that if d is less than 001, within the for loop is executed, like hundreds of millions of times per second.
Yeah.
That's why buy really hard, really expensive GPUs, so they can do that.
Yes.
Exactly. That's why we love NVIDIA.
AMD's good too.
Yeah. Oh, sorry.
Don't bring the GPU war.
RTX 2. I agree. They're a great graphics card as well. That's why we love graphics cards.
So I set a boolean here, and what I want to do is colored my pixel, okay, as we said, based on do I hit something or not. So if I hit something, my color equal I call it color equal, for example, my shading, because I hit something, so I want it to be shade. Else, so if I don't hit something, make the color black. Okay? And I hope I will not have any error, and I have it, and I have one. Hey. Ah, yes, because shading is a float, so I need to do some swizzling to put it back to a vector free.
You could also add a color to.
Yeah, I can
Well, we're going to
also
do that
add
in a minute,
color.
I'm sure.
And
Keep it simple.
yeah, what I did, color, if I hit color equal vec3 shading, for shading is my iteration divided by 100. It equals true here, it equals false. So, what the fuck?
So you need to return the
no,
color.
I'm sorry.
Oh, no.
Yes, I have it. I have my sphere here. I just need to inverse the shading to make it more white.
Oh.
Okay? So I have a sphere.
Yeah, come on, Bruce. We've been waiting for this.
So now you can enter the shader showdown. Okay, so I have a sphere along a remarked sphere.
It was shaded from black to white rather than white to black, basically.
Yes.
So that's why it looked sort of. But it might be the look you're going for, by the way, if you want something to be sort of see-through or something.
What I can do now, for example, is showing you the same trick as we did before in 2D, is multiply it in the space. So it's exactly the same thing. It's just modulate the p, modulo p. You know, the p is the position, equal modulo of p with a period of, I don't know, maybe 2. Yeah.
Let's try. As long as it's more than the radius.
Minus.
As long as it's more than the radius,
Yes.
essentially, because you don't want to repeat, well, unless you want colliding geometries, but obviously what we're doing here is doing infinite cloning. Modulo is quite amazing in what it can do, in that you can just create infinite geometry like this. This is just a sphere that's being multiplied along every single axis, X, Y, and Z, by the way.
Yeah. But you can do in just one axis or two, or as you wish.
You can.
Okay, so you have an infinite field of spheres. Okay, and maybe what we can do now is make the spheres bouncing like that, maybe growing up and down.
Yeah.
It might be fun, and it will be doing via, by the radius. So here we have a radius of 1. If we add a sinus to it, which came from -1 to 2 + 1, and I need to stop. Okay.
From the organization, we would suggest that we make a break and get air into the room. Would that be okay for you?
Yeah, okay.
That's cool.
Okay.
Yes,
Okay,
good,
then
great.
we'll
So-
start a
What, 5
pause
minutes,
of
10 minutes?
at least 5 minutes.
5 minutes? Okay, sorry, we
Okay,
were
guys,
too long.
yeah, get some beers and
Get
stuff.
some beer and get
Yeah.
some fresh air.
Come back
Okay.
in
See you
5
later.
minutes. Yeah, cool.
Thank you.
Okay, part 2. So I think we will stick to what we've done here, and maybe adding some proper lighting to it, because right now you are seeing just the iteration on the spheres, the tricks to display your shading, your shapes quite quick. But maybe doing a proper lighting will be great. And to do proper lighting, you need normals.
That's right.
And you don't have normals right there. You need to calculate it.
So normals are like
Normals are like the perpendicular vector to the surface. And in 3D, most of you will know this, but essentially in 3D, let's take my bloody electronic fucking cigarette right here, Brewski. And the normals would be on the surface pointing like this. It's like the perpendicular vector to the surface. And in 3D packages, again, C4D and all this stuff, you have faces. We don't have faces in ray marching. We don't have vertices. But we can get the normals anyway from getting the perpendicular vector to the actual surface. But I'm just saying, making them image that in normal 3D packages, you would have a face, and a normal generally is at the center of the face, like that. Okay? And yeah, I know. Very sexual. It's cool. It's Sunday. We're at a demo party. It's all good, bro. But yeah, all we need to calculate lighting, and it's the same in 3D packages, like C4D, whatever, is the normals, because then we do a calculation from the light direction to the normals, because the normals tell us which way a face is pointing, right? And then we bounce the light off that. We calculate the bounce of the light on the surface, essentially. Just wanted to clarify what normals were generally in 3D and stuff.
Okay, thank you. And to calculate normals into a remarching, you need to do something I will draw in paint again, so be prepared. Okay, oh no. Okay, so imagine you eat there, you eat this spot, and you want the normal to this spot, this one, okay, right there. Okay, this is the spot where you eat something and you did the normal to it. Maybe I can use blue. Blue is visible, yes. And what we do to calculate normal is to do the difference, so the distance basically, between this position plus a little value and this position minus a little value. Okay, so we are calculating this distance and we are doing it for each direction, so x, y, and z, and it will give us the direction of a normal. Okay, just calculate it. This little epsilon in each direction will give us the vector which is perpendicular to the surface we hit.
It's like making an average. By the way, I've never had this explained to me as good as this. This is fucking brilliant. I've never actually understood the normal function. But this is going back to what we were saying. Sorry, I don't know your name, but we were discussing before about the code, and sometimes I'm just like, guys, I don't understand this. I'm okay. I'm pretty good at doing shaders still, and it goes back to that point, though. Sorry to sort of try and drill this into your heads, but a lot of people are scared of or not scared, but they're like, fuck doing ray marching, it's all 3D stuff, it's so complicated, I don't understand the math. And you feel like, and I hear you because we're discussing this, you feel like you need to understand everything. And I think in ray marching, it's good to let go a bit with that. And for example, up to today, up to now, flopping now, just explaining this, I had never understood the normals. I'm not lying. I'm not even lying, guys. All I know is that I found the code on Shader Toy, and not just that, I do 4K intros, so I do size, small size stuff. So I didn't just find the code on Shader Toy. I found the smallest normals function on Shader Toy. It's not, I don't deserve a medal, it's easy, but I'm just saying I looked out for a very small version of it and I found out that actually it works really well. I got really good lighting out of it, so that's cool, but I didn't ever understand actually what it does. All I know is it's 3 lines of code, I can copy and paste them, that gives me normals. Now I know what normals are and I know how to fucking use them to do lighting, but I didn't understand up to today how to calculate them, but I knew there's a function for it. But a lot of stuff in ray marching is about that. It's about finding that bit of code on Shader Toy that does that one thing you want to do and knowing how to use it, not specifically understanding it. Because when you start doing complicated bump mapping with derivatives and blah, 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 or the shit, whatever, unless you're a math genius like Floppin, if you're an idiot like me, you'll be lost. And that's cool. It doesn't matter because you can still do it. You can still use it and it still works.
Yeah.
Let the geniuses do the math, bro. And don't worry about it too much.
That's 2 different approach.
Yeah. No, but this is great because Floppin is now explained it to me. Do you know what I'm saying? It's a great example.
There is a lot of things I did not quite well understand, but I think as Evil said, the purpose is just to have enough knowledge to understand what you are doing. It's just like that. Maybe you.
That's right. If you're doing lighting, you need normals. If you need normals, there's a function that calculates them from a position. So we are now going to create a position. Well, as in she already did, but we just need to track where we're at with array. We know where we're at with array. We know what the surface is. We use a function with those two inputs that gives us an output of normals. Cool. Now I've got normals. I know how to do the lighting. Do you know what I mean? It's like that. Well, I didn't before, but I found out that you take normals and do a dot product with the light direction. That's how you got lighting. That's what we're about to do.
Yeah.
It's amazingly simple, actually.
Yeah, don't be afraid. That's what you want to say.
Yeah,
I
that's
think.
right. Sorry, it took a while to get it out.
No, but I say that because I learned from a person who said to me, and I think is also right. That's just two different sides of it. To understand what math functions do, help you to use them maybe in a way that are not thought before. You know.
That is also a very, very good point, and I totally agree with it. And in fact, I would extend on it, which is that, I have been doing ray marching for a while, and it's some good stuff, but maybe my best stuff has come since I have a better understanding of actually what those functions do, because I can tweak the inside of it, and in some cases it's very useful. But still, I would still go back to my point as well and say that at a beginner level anyway, just don't worry about it too much. When you start going really advanced into shit, then you should really understand it. And for Shader Showdown, for example, I do a lot of stuff from memory. And I found out before that I did not knew this normal function or whatever, I wouldn't really understand them. Therefore, I wouldn't really be able to memorize them well. And that's a very good point. As in, like, I'm get a lot better at the Shader Showdown since I understand what these functions do. Because if I make a typo mistake, I already know the concept of how to fix it. Rather, do you know what I'm saying? So I think they are both extremely valid points.
Yeah. Knowing what you're doing helps you to not having to memorize it because you understand what you're doing.
Right.
So
even if I forget the normal function, I sort of know how to rebuild it back because I understand the concept of it.
Yeah.
Well, actually, normals I was lying because literally I didn't know it till today.
So to calculate a normal, so you need to have this little epsilon backward and forward in all direction, and so we can code it as that. So vec3 get normal, for example, this will be our function, and we will need the position where we are. Okay, so now I just want to declare, I will use that. I just want to declare a vector2 which will be the epsilon. You know, you know the
It's all
okay. The epsilon I told you about. You need to go forward and backward to have it, and just calculate this distance. You know, I am basically coding this stuff. The blue stuff right there.
See epsilon as the blue stuff. So we have to. This is my not so good math brain, obviously. But it's just basically a value which is quite small and will mean it's like 0 now. You hit it. It's like that number we had where d is less than 0.001, and epsilon is that 0.01 sort of thing.
Okay.
In our normal's case.
Okay, so normal, as it says, needs to be normalized. So it means that it needs to be between 0 and 1.
Yeah.
So all the value, for example, you are between minus 200 and plus 200, those value will be shrink to enter between 0 and 1. It's not cutting the value, okay? We keep all the value, but just normalized it between 0 and 1. So normalize.
So it's like mapping the value back.
Mapping.
Yeah,
yes.
to 0, 1 sort of thing.
So
if you have a value from 0 to 150, we now just make it from 0 to 1 with the same sort of precision, just scale it differently.
Yeah. So usually you normalize vector 3. And this vector 3 will have the value of the length between those epsilon. So it is coded as my 3D world. I am calling here my 3D world sphere. For now, it's sphere. Maybe I can call it map.
Yeah,
Yeah, maybe make a map function
Map.
actually, because we're gonna add a few more shapes as well. So
And just my map return my sphere.
Yeah.
It's
So-
just map is my environment and it's
Yeah.
calling sphere, so I have one sphere in my environment.
You should see map as really your scene. And just again, a side note about Shader Toy, you will see this on Shader Toy. This is like a general rule of thumb on Shader Toy. People put your geometry, your shapes are in a map function. I insist, this is quite important. Especially because you're gonna go home, you're gonna go on Shader Toy and go, let me check this out, and then you're gonna be like, what the fuck's your geometry? Like, because obviously in this shader code you have a bit of the code as for the geometry, a bit for the lighting, a bit for that, a bit for this, a bit for the UVs, as you're now finding out. So when you're looking for the geometry definition, the distance field, the actual scene, the actual geometry, generally people put it in a function called map.
And I pull it in a function called
Yeah,
SDF, but
and she calls it something different. So yeah, there you go.
if you watch mine,
Standards are meant to be broken, especially by French people.
oh,
I'm French as well.
yes,
it's
you
okay.
are as French as me. SDF. Okay.
That's so brilliant.
So first of all, I call my map once, and I want to have my environment in the position plus my epsilon. So P, position, plus my epsilon on x-axis. So I am calling my variable epsilon and calling it like that. Epsilon point x, y, y. And this is doing swizzling. What I basically do right there is creating a new vector 3 with value 0.001 on x, and then 0 on y, and 0 again on the third value of my vec3. Okay, that is called swizzling. Okay.
Yeah, it's like making a vector 3 out of a vector 2 by repeating one of the axes.
Yeah.
It's like going from 2D to 3D by just brutally forcing one of the axes on another. Really, you should see it like this. It is X, Y, Y. So usually you get X, Y, Z, right? But what happens if you don't have the Z, or for some reason you don't need it, you can just push the Y onto it, and that's exactly what we're doing. And you can do, obviously, X, Y, Y, you can do Z, Y, Y, Z, X, Y, X, Y, Z, whatever. You can do X, X, X. You can, it's crazy. It's called swizzling.
And
sounds
again,
fucking cool, like a hipster coffee thing,
and again, it's just in GLSL. HLSL don't have that.
What do you mean HLSL don't have a swizzling?
HL
sound to differ, do they? No.
No, for example, HLSL, at least on Unity, you can't say vec3.1. You just have to say vec3.1, virgule 1, virgule 1. And it's just so boring.
Yeah, well,
It's awful.
no comment. Let's move on to the next bit.
So, as I said, you need to calculate the length between the epsilon plus the epsilon minus the epsilon. So calculate a length between 2 points, it's just doing the minus of them. So my map of P plus my epsilon minus my map of P minus the epsilon. And what I did right there is just calculating that, okay? For the x-axis, this blue line right there. And I need to do the same for the 2 over axis. So basically, you just can copy-paste here. Up. Just get rid of the last comma, because you are at the end of the declaration of your vec3. Maybe I can...
That's enough data for one function. Come on, guys. It's Sunday as well, we're all hungover.
So that's the parenthesis of the vec3, and that's the parenthesis of the normalize. Okay, just for you to follow the stuff. And then on the other... Oh, sorry. Oh, no. On the other elements, you just have to push the x in the x of the epsilon on the right axis. So here we are on the y-axis, so I need my epsilon 0.001 to be on the y, etc., etc. And here we are on the z-axis.
We're swizzling again, guys.
Yeah.
Hang
And
on to your
that's how
seat.
you get normal. And now I can just put it in my color. So for example, if I hit something, I am using the get normal function with the position I hit. And I have normal.
So that's showing you the normals as per sort of real-time toolkit see them, and when you draw them in other packages, they look like little arrows. This is little arrows in a shader. You should see it as, if you're in C4D, you click on seeing normals, you'll see all these little white things pointing up and outwards from your geometry. That's the equivalent to that, because it's represented by RGB values.
Yeah.
But yeah, if you're seeing this, it's all looking groovy, broski. I mean, obviously it doesn't look like lighting yet, but that's the normals we need for the lighting.
And as I said at the beginning with the 2D UV and the colors, X is on the red, represented by red, Y by green, and Z by blue. You can see a little bit of blue right there. Okay.
That I was always confused about. Another thing you learn from coming here.
Yeah. You will learn a lot.
Yeah,
it seems.
I already have. It's mind blowing. I'm here to help you for a workshop. I'm the one learning all the stuff.
And I will just code a quick box to show you the effect on normal. Maybe it might be better because this epsilon has a huge impact on the normal, but I think spheres will not be as...
Also, we want to show off our map function, and I was about to add that basically, if you're confused why we created a map function, it's because, well, generally when you make a 3D scene, you'll have more than one primitive call. So before, because we was just displaying one sphere, we had our map function, but it was just calling a sphere only, so we just called the sphere function. But in terms of organizing your code, I do recommend doing this, guys, and you will see this all over Shaded Toy. Make a map function, put your geometry in it, right? So we've got a sphere, but can we show them very quickly, not even a smooth min, but just we'll do a little operation of adding geometries together so we can have more than just a sphere and just have some boxes as well, basically. But the idea is that your map function generally is, quite complicated. You'll have complicated in the sense that if you want four spheres, you'll have 4 sphere calls there. Yeah, and then, you can very, very easily add shapes together. And again, see what we were talking about, and I was saying that I don't really understand some of these primitive functions that well, but I still use them. This is another good example with the box. This function creates a box, and all you need to call it to understand sort of is that, well, every box will always have a position, and then it has not a radius as a float, but you should see it as a radius on every axis, which is basically your box width, height, and depth. And it's effect 3, and it's literally, width, height, and depth. And, I sort of understand it by now, which is it's just a limit function. Oh, if it's less than that, and it draws the box. But I'm still confused by it, and it's still cool. I still use it. Do you know what I mean?
It seems that I'm not able to code a box anymore because I don't know.
Actually, it's just max of q.x, q.z. I don't know about this min stuff.
You don't know? It's for having a signed box.
So she's doing the more
box.
analytical box function. No, it's funny because you see those different functions on Shader Toy, and I use what I call a cheap box function, which is just basically less code.
I'm just stupid. I am filling my distance with sphere, not with map.
That's why.
That's why. And I have a box. Okay, I'm not that stupid.
There you go.
I hope.
She actually understands this shit better than me.
Okay, I have a field of boxes. And now I can also have a field of
Spheres.
boxes with spheres, but it's not really see. Okay, just give me a moment.
Right, so we're going to.
Okay, I have box and I need spheres, and here I have also spheres in
Yes.
the box.
Yes. So we can just explain this. Let me just explain this
Okay.
quickly. So this is very actually important because this is the first time we mix geometries together, and you're gonna want to do that. Is my guess. You're probably gonna want to get more than just a sphere on the screen, and this is very important. This is how we achieve our shape and our map function, that's the reason for it. It's because we always going to get a sphere and a box and another sphere and another fucking tetrahedron and whatever you want. You put that shit in a map function. All you need to know is that when you want to add shapes together, you just basically use min. It sounds sort of simple and sorry, I think it's okay. Maybe it doesn't sound simple. Sorry, I'll take that back. But it's actually really is, because what I'm trying to say is that this is where ray marching is really good at, and compared to 3D packages as well. Is you know how that shit is to do in C4D. You do the booty operation, and sure, it works good enough, but you get fucked up faces in most cases, or you get like overloaded geometry, or you have to really crank up the number of polygons and stuff. Now, in ray marching, you can add a sphere to a box. You can go, hey, box minus sphere. You can do that in real time. Like, it's so crazy because this shit is so hard to do in offline rendering. No, it's not hard to do. But what I'm saying is, it's not hard to do because you'll have a Boolean operator in Cinema 4D. But under the hood, what it does is actually, crazy complicated. Whereas what we do is just take the minimum between two numbers.
To distance.
That's it. We have a distance of the sphere. We got the distance of the box. Get a minimum of them. Guess what? That adds them together. That's all you need to know. Guess what? We're going to do quickly removing them. Intersection. And that's it. Look, I'm sure you guys know about some of these 3D packages. They all have them. 3ds Max. They all have them where you can go, oh, I have this box, but I want to cut out. This is what we're doing, yeah? We're cutting out a sphere from this box. And you do it with a booty operation in C4D or whatever, similar stuff in Houdini, whatever it is in 3ds Max. But it's classic shit, yeah? It's just that we can do it so easily here. All you need to know is that to add, you need to know them as additive, subtractive, intersection. That's sort of all you need to know. So adding geometry together is just a mean function. Now, if you want to remove geometry, subtraction, right, would be using max with a minus. But watch this, it is so actually simple. So this is to add geometry, and as you can see, it combined our box and our sphere. But if we do this, we can, do subtraction. It's this.
Tu veux que je tape?
Non, je vais le faire vite. And so, for you just need to know them, but there's only 3 to know. I know all of them by heart because there's only fucking 3. I'm not that clever, but it's just minus, isn't it, for the intersection?
Yeah. Yes, but
sorry, compile.
So you need to compile, but it doesn't.
Sorry, return.
You have to return.
Yeah. Let's just remove that, and there you go. There you go. Now we have
Holes.
you have basically holes. So it's subtraction rather than addition. Now we start seeing some blue artifact and all this. We might touch on that in a bit if we got time. But that's the problem here is that the geometry has become so thin. I'll just highlight this for a second. This is a side thing, but still. It's looking a bit fucked up, yeah? And that's because basically now, think about it. The surface is so thin on around these bits on the outside, the surface is so thin that when we step forward, the ray steps from being before the geometry to after too quickly, and it goes, I don't know where the geometry is anymore. I don't know if I'm inside, outside, or anymore. And that's when you get artifacts. And again, I would argue this goes back to, sorry, I was discussing it with a few people during the break, where we are discussing about ray marching, and I said it's good to know the limitation. What I'm saying here is, you happen to have taken a box and put a sphere to cut it the inside out. And what this does is that some of the surface is so thin that we can't render it. So how do you fix that? But don't fucking do it. That's how you fix it. Don't do it. I mean, sure, you can raise the step count to something crazy, and you may get something all right. But I'm being honest. In this very specific case, this is sort of a rendering nightmare, and you're never, you got to be very careful with these sort of scenarios when you're better off, rather than fixing it, just change your design idea. Don't do it. Don't do it. Do something else.
If I can say something, it's not always working, but I have a tricks to avoid that.
I know where you're going with this. This is a classic ray marching trick, by the way. But yeah,
a classic ray marching trick. It's to march slower.
Yeah, that's right.
And then where you put the p, when you add your variable d to the p, just multiply by, I don't know. I'm sorry, I'm not in the right place. Multiply it by 1.8.
That's right. So we're doing this. We're like, do you remember when I fucking jumped like a dickhead like that and just landed where the geometry is?
And I have less and less
artifacts. We're jumping a little bit less close here. We're jumping kind of close to it, but we don't want to overstep it, because what we're doing here is basically overstepping it and going like, shit, we went through the geometry without registering it, sort of thing.
Yeah, but as you can see, as I march slower, I can go less further. Yeah. So that's why my field of cube is cutting.
You can also, sorry, I don't know if it's going to work in this. I'm just warning in case I'm like, oh, this is going to be great, but then I totally crash. So warning, it might not work with this setup. But you can also raise the definition of your distance field. This is another very, very, very simple trick, which a lot of people use. And it would be, for example, we go in our math function, and you know how we've got that sphere and we got that box. Now, this may sound a little illogical, but I'm going to raise the definition of it by multiplying it by 0.7. You'd assume you'd have to go, I don't know, in my dumb math brain, I was like, surely if I want to raise the definition, I should multiply it up. But actually, if you multiply it down, you raise the definition, and you should...
la box.
Yeah, and both, and this as well, in fact.
I'm multiplying all of it.
Yeah.
It's not the same thing.
I don't. Yeah, it is. In fact, you're right. Sorry. It
mathematically, no, but no problem. Yeah.
Okay, whatever. Let's just, because the reason why I do each individually as well is, get this. Some scenarios you multiply by 0.7, some 0.8, some 0.9, and what I do is I tend to just do it by eye. And you see that it's gone better, didn't it? I think it's become a bit better. Oh shit! How do you?
Do you want me to type something?
Yeah, maybe. Hang on. No, yeah. Shit, I don't know, man.
We are already in a worst case of that.
Yeah, I mean, this is fixing stuff, but you're gonna have to do this. It's good that we mentioned it, Flopin, because, I've had loads of people talk to me about ray marching, and they're like, it's just everything I do looks so shit, everything's so broken, and I don't know how to fix it. And these are the little tweaks. Well, all I'm trying to say to you guys is, so I would argue that a combo of these three. Can you maybe remove your ray marching step thing? Yeah, and then do what I did, on the shapes. I'm actually super curious to see what the difference is. So multiply the box by 0.7, and then here as well. Yeah, Yeah, so it's do it like 0.5, let's say. Just indulge me. It's not really working. I think this is like the worst case scenario. Honestly, like
Now, if you quickly retract to see that level, okay, that's right, then maybe you take the absolute of D. So when you step through the surface, you still land on the outside.
that's interesting as well. And I think that does like a pseudo fractal bullshit thing, which is very interesting.
Now we are really in the worst case scenario.
We are. It's like we shouldn't have done this, but it's
I need to
interesting.
take the
Do you know what?
absolute
It's
right
really
there.
interesting actually to highlight that point
Yeah.
I was trying to make out, which is know the limits of ray marching. What I'm saying is that I've had guys on Twitch that go, "Oh, can you fix my shader? Can you can you somehow make it look better because you know your stuff?" And I'd be like, "Bro, you're displacing everything so much. Like it's
Exactly.
never gonna work.
It's-
It will never be fixable." So, well,
Sometimes helps. Not always, but sometimes it helps.
yeah.
Yeah.
But okay, so just to finish on this thing, what I'm trying to explain is that in cases where you get some ugly artifacts and shit like that, I tend to fix it either with Floppin's trick she just showed, or by literally your box function call, your sphere function call, yeah? These function calls you make where you call a sphere, you call a box, you call a tetrahedron, whatever it is, you have that in your map function. And I'm saying to you, you can do this also on that level, on the map level, which is inside the map function, wherever you call sphere or box, multiply it by a number less than 1. Now get this, and this is quite important. If you were to scale P for some reason, I'll give you a very simple reason. You're doing your scene and it's massive. It's like you want it this big, but it's like, I don't know, even 10 times bigger, and you're like, this is shit. Like, okay, I can move my camera back, but it's not working. Like, everything's out of scale, and it's just nuts. What you can do is just go here and call P times 2. P times 2 will make it actually twice smaller. But if you do that, you have to then tweak the domain. So this is where you saw me do a 0.7 because I needed more definition. Yeah, if you get artifact, that means often you need more definition. So you do 0.7 on the sphere or 0.7 on the box. But if you've made the whole scale of the scene bigger, then you might need to scale it up. So if you do P times 2, you might actually need to do this times 2 as well, just to sort of tweak the domain. These are real quirks of ray marching, but sort of trust me when I say these are invaluable tricks for you to actually make stuff that actually looks good as well, where it doesn't just look completely
I think
shit.
it's the opposite about the scaling factor.
Yeah, sorry, you're right, by the way.
When you scale
Times
up,
by 2, you need to divide
divided by
yeah,
2.
Yes, sorry.
When you scale your position by 2, you need to divide the distance
That's right.
by the same number. Okay. This is the position. This is the distance and when you want to scale up things, you scale up the entire space. In fact, but as you scale up the entire space, you want to. As you scale up the entire space, you actually want to fill the distance in the same amount of space. But just having the space twice bigger, you have to divide the distance by 2. So yeah. Tu veux que je le fasse? You want me to? Oh.
It's fine.
Yeah.
So now if I do this, you see we scaled, it's gone crazy.
We scale the space,
But
the
now
entire
if I-
space.
Now if I do this, so it's 0 point.
Whoa! You're not. Do you want me to?
Yeah, please. French keyboard, man. Jesus.
Okay, so now I am divided by 2, and it's basically approximately the same because we are repeating the space, but at least I don't have this crazy mush of pixels because I kind of normalized the operation. Okay, what is done that multiply by 2 and divide the distance by 2 is it's like normalizing the transformation. Tu t'en sors?
Yeah, I was
Maybe
just
we
trying to
can.
show intersection,
Oh,
which doesn't work in this case.
because you say min minus.
Yeah.
So this is
yeah.
the intersection, and it's just max. The
Oh, it's just max, sorry,
Yes,
yeah.
the intersection is just max.
Yeah, good point.
And you have the intersection between the sphere and the cube. It's just max. Okay.
And man, to be honest,
Guys, you can do a lot of fucking cool shit with that already, you know? I mean, all the stuff that you can't sort of do in, well, you can, but it's just a bummer to get the vertices and the faces to not collapse in some of these operations when you do these in 3D packages. We don't have this problem in ray marching. And I insist on that. You can just go sphere minus cube, cube minus spheres. We can do that. We can do cube minus sphere minus cube plus minus. That's exactly what the mean function does, guys, yeah? So when we see these things here, max, you can keep going. Let's just do one. Can you type add a box to a sphere and then remove another sphere? And it was just going to be, it's not going to be super readable, and you might go like, what this thing again? But it's actually super simple. We first do a min of 2 boxes, and then do a max of that. Do you know what I mean? So what we're doing here, oh shit, that was a bad idea. What we do is add a sphere to a cube and then remove a cube from the whole thing, basically. And, it's just chained operations. You know what I mean? You could just keep going. Basically, when you do really complicated ray marching thing, you do exactly this. You do max, min, max, min, max, min. Generally, what you do is build a function for it. You will build a function called, so IQ calls them operators, like OP, what is it? OP.
And I just bring back a hole, but it's all glitchy. So
we was talking about this as well. All these functions are on IQ's website. So for those of you who don't know, IQ, whatever it's called, IQ is like a ray marching master who has a lot of the theory behind, I guess, and implemented it really well. He's the guy who started Shader Toy, and he's got a page which you can find when you just Google ray marching modeling.
Maybe we can show them stuff like that at the end of the workshop continue the train. You know, if you want to go further of what we want, we will give you some links.
Just wanted to, so you don't like panic and go, shit, I need to remember this min-max stuff. You don't. It's all on the website, and it's really well sort of all laid out. Well, he's not much of a graphic designer. IQ is he fucking hell. But
it's finished in 20 minutes, and we need to do lighting. So
okay. Oh, sorry, she's keeping me in check, which is great. I need that. You keep going, girl.
Okay, so we have our normal, and now we want to calculate the angle, kind of, between the light and the normal. As Eviville said, you need to bounce the light through the direction of the normal. And for that, I will call a function, which is called lighting or something like that, as you want. So lighting. Oula.
Call it diffuse because we're gonna just do the diffuse dot product.
Okay, if you want.
So diffuse is like the most basic type of lighting, which you should see as the sunlight. So
it's more directional lighting, yes.
That's right.
Directional lighting. That's what we are we are doing right now.
Yeah.
It's the diffusion.
So essentially, in a sort of comparing it to a real world environment, what we are doing here is we take an object and we leave it outside. Because if you're outside, you always have a directional light because of the sun position. And it actually, arguably, it's a point light, but it's just so far away from us that it becomes directional, if I had to say about the sun. Is
Yeah.
that wrong? Or
Yeah, kind of.
okay, cool. Sorry, boys, girls.
For calculating the lighting, we need the normal and the lighting. That's why I called two parameters, vec3 n for normal and vec3 l for light. And as I said, we need the angle between those two. So an angle, mathematically it's more the cosinus of the angle, but still the orientation, the angle between those two vectors are calculating through a dot product. And what I need to do is dot product between the normal, so n, and the
And the
normalized
light.
value of my light, just to avoid having a power of light which might be, I don't know, 2 or -1 or things like that. Okay, just
Yeah.
normalize the light is important. And to bring all again, to avoid negative value or stuff like that that might be rendered really weird, I'm using multiply 0.5 plus 0.5 to bring back all the value and avoid because and
Interesting. I do it
yeah.
differently.
I can use max 0.
Yeah.
But I think max 0 will just cut the value, while it's approximately the same. But max 0 will cut the value. This will just raise up everything,
Yes,
because a
it's
dot
very
product.
interesting, actually.
But I think maxing it and testing it against zero avoids that you get weird things when the light on the other side, where the cosine would be negative, then you don't want the light to shine through, and you really want to.
This too, because the dot product is between -1 and 1. So multiply it by 0.5 and adding 0.5, put those
It
values between
normalizes
0
it
and
somehow
1.
as well. No, I'm just saying your approach is very interesting. I use max 0, but I think
It's good too.
I'm not sure if that. I never used it like that.
So a dot product is between -1 and 1
Yeah.
each time, okay? Also because we normalize the light. So this is between -1 and 1. So if I multiply that by 0.5, take the -1 example, the lowest, it's
Yeah.
the minus
Minus
0.5
0.5,
plus
yeah.
0.5, 0. And it's doing that for all the value.
I'm gonna test this out. This is super interesting because
I'm not sure if that then would be like physically correct. I mean, because you just it depends on what look you want to achieve. Because that would mean that you would kind of ward the light, the lighting that's coming from the backside that you don't want, pulling it on the other side. Although you usually want to just cut it off and say, well, my surface is opaque and I don't want light to shine through.
These techniques will help you having a false second bounce of light. It will raise up the color of the shadow a little bit. It's just it's the fake indirect lighting.
Okay,
Totally fake indirect lighting, but it's also a trick to avoid negative value. But it can be also used to do a fake indirect lighting, really basics, not the.
You're trying to get two lighting spread
Yes.
in one go, right?
Yeah.
Okay, yeah.
Oh.
Cool. Yeah, very well.
What
Very
have
cool.
I say?
We got 10 to 12 minutes.
10 to 12 minutes? Okay, okay. So I have my diffuse, and now I just set my color as being my diffuse. So I just need to add brackets because I will write more things in the condition. So this get normal will be my vec3 n. Okay. I need a light. Vec3 L equal, I don't know, I can position, this will be
So,
the
yeah,
position of my directional light. I can do
yeah.
like 1.5, 2, and -0.3, for example, -0.2, because I am I am in the back of the scene. So if I put my light back 2, I will have some kind of
Yeah.
face lighting. If
Yeah.
I put my light in 2, I will have a rim lighting. You know, with so you
it
will
depends
be.
what you're going for, obviously. But generally, in terms of even, I would advise for you to do your design, and so you can see shit really well. Always sort of put the light behind the camera, shining straight or on the side. A bit actually is really interesting on the side. Just saying, for those, there was a guy asking before as well about how the fuck do we choose these numbers and stuff sometimes, and we said trial and error obviously and experience, but sometimes as well you just want to do things so that it's clear to you. So what the Floppin's doing now is like, you got frontal sort of lighting so you can see your stuff. I'm not saying you should use this in the final product, but when you design it, make it easy for yourself so you can actually see stuff.
Oops.
And not have the light against you, the camera, and then it's all dark,
You
and
see
then
the
you're doing your whole
difference?
thing, and then when you switch the light back, you're
that's
like
max.
seeing all this detail.
And so that's the max. I don't know
Let's
your
compare
name.
it.
I'm sorry.
Yeah.
Next, that's the max you're talking about. So yeah, you can see that we avoid negative value, and then everything is zero when you don't have light.
Yeah.
And the technique I used just bring back some
Some detail. Wow, this is cool.
second. It's
Oh my god, this is going straight in my shader showdown routine against you.
wow.
This is really cool because this is sort of a backlight, as we would call it. Fake, but
totally
sweet.
fake.
Sweet.
Second rebound.
You're right though, as in, sorry,
Yeah.
you are both right. That's the funny bit.
If you want to do that and want to do it
That's right.
with code, then this is certainly the approach to take.
That's right.
I
That's
was
right.
going for more
Y-
glitch phone, which
Yes,
You're right.
the
You were
blink phone,
going
yeah.
about physically correct approach of
It's
lighting.
totally not
Yeah.
physically
Yeah.
correct. You're right for
But
that.
it looks better. Well, in this very particular scenario, it looks better, and it's very important to know these tricks. You see what I was saying? The ray marching is about knowing all the tricks and pull them out when you need them.
Okay, so we have proper lighting, and I just want to show you another kind of tricks that is more called hemisphere lighting, which is just using this light information as a mixing mask. Sorry, as a mixing mask. So as you can see, sorry, it's white and black value. So it's basically 0 and 1. Okay, and you can use that to mix two color to have, for example, the shadow part being, I don't know, blue, and the lighting part right there being orange, for example. And you can just do that with one line of code. In the moment you have the directional light, it's just mix, okay, between two colors, so two vec free, basically. Okay, vec free, and I don't know.
This
Between,
is just like setting your colors again in 3D packages or even in toolkits like Unity or whatever, where you could set your diffuse color, your sort of your diffuse black. Sorry, not black, but okay, let's call them dark and light colors. And we can do that again in ray marching as well. So.
And now you have,
Exactly.
that's not the best
Well,
lighting I
but
can do, but
still it works though. I mean,
yeah, that for example. And it's just basically using the mix function, which take the value, one value, another value, and the masks you will use to blend them.
That's
so
right.
when the diffuse directional is at 0, it will took this value, and if it's the value of diffuse is
it's
1.
it's like your albedo color almost, and your like shaded albedo color. You should see them as like that. It's the color you want to apply when we are darkening the geometry, and the color you get when it is fully lit. So
And
I
this
guess.
is what you have when you do max on the hemisphere lighting. So I think, yeah, for the purpose of shader showdown or things like that, it might be
she's
better
right.
to use this
She's
one
right.
that will bring back a little
Yeah.
bit of details right there and right there.
I'm gonna add just for fun and because it's so easy to do, and because I'm gonna add
gamma
some
correction?
quick fog. I was
Oh,
just
no.
well, gamma is a good idea
Gamma
actually.
correction.
I'm just
You have to. Do you want me to type things?
Yeah,
maybe?
please.
Because
You
it's
do
a
it.
French.
You know how to do a fog, I'm sure.
Oh no. So for a fog, we need the distance between the origin and where we are to have some kind of Z buffer, as you said. We need this distance. And then we just do color equal mix again. between itself, so being just the color, vec3, which will be the color of the fog, and with y minus exponential, and it will give you a fog.
And you know these, you know when you're in Unity and all these
Mr. T
fucking
by
things, or in like C40 and stuff, and you change your fog, and you change from like linear fog to like exponential and exponential squared and all this stuff, and you're like, wow, this is so great. I'm buzzing. Like all it's fucking doing is
Okay.
changing the actual fog function from exp to a mix or to an exp2. Literally, that's, I'm pretty sure under the hood that's what it does. Fog is one line of code. It's so simple. And I mean, in most cases, to be honest, in most 3D scenes, unless you're doing a very inside 3D scene, like, oh, this is a room and we're inside this room. In most cases, you should probably have fog in your scenes. You know,
And-
it really helps
And this
so
value,
much in many for many reasons. Also, with ray marching, fog is so brilliant because, as I said, you can optimize it by going like, "Hey, stop shooting the ray past the fog," and then it's like super well optimized.
there is a
Because,
question right
oh,
there.
sorry, yeah.
More. More sphere and cube? Okay, this value right there is the distance of the fog. So right there, it's really near me. Morph. Yes, yes, we can do that. Yes, totally.
Andrea, she can, I can't, Brucey.
Okay,
I can guess where she's going to do it. Let's see.
Okay, morph between a sphere and a box. Okay, so return mix between a sphere.
Yeah, it's that simple, isn't it?
Yeah.
Why was some guy winning the shader of the week with it, like last month?
I don't know. I maybe I'm not the right. I'm just trying something.
No,
Okay.
I'm hearing you, but if it's that simple, then why did you
And
win shader of the week?
you can do scene of
Yeah,
time.
that's how I would do it, but I would be totally winging it. So. And it's totally working.
Nah, it's not working pretty well, but maybe it's because I have this and I have the p multiplied by 2.
Yeah. Wow, sweet. That's simple, broski.
And
You see
it's
what I was
because,
saying about ray marching doing crazy bullion and stuff?
I am between the sinus goes between -1
Minus
and
1 to 1, so we need to
So to raise it, I can do
normalize
the
it or
same
whatever.
as I
Say, do the same 0.5 tempo. Yeah.
and you
There
move
you
your-
go. Not even 5 minutes, bro. What was that? 1.5. Come on, bring it. Yeah. Nice one. That was great. That was great.
Once you basically understand what a function do, like what mix do,
Yeah, right.
taking one value or the other between a threshold
Yeah.
you took, you understand what it does, so you can use it on everything, on lighting, on
That's
shapes,
right.
etc.
And that's sort of where, when people ask, can we do this? I was sort of like, wait a minute, can I do this? And then I was thinking, well, yeah, because in theory, you should see it like this. Your sphere, your box, is a float. It's just a number. It's a distance, right? So it's simpler than a 3D shape in many ways because it's just one number. Your sphere at this place where it's at, where you put it, is represented by a number. Your box is also represented by a number. So what? We can just
mathematically, you can do
literally,
everything.
we're lerping. You know, lerp is like a direct text expression, linear interpolation. So we're essentially mix. Mix is a function which takes a number and another one, and then it goes from 0 to 1. That's why it's called mix. It's like having a mixer, you know, where you mix records between one number to another. It's a fader that goes from one number to another,
And
one input to another. But our box, our sphere, they're both a number, right? So we can morph from one to another by just mixing back and forth from a function.
And
So I
what
just
is
wanted to
fun-
say that's why it's so simple, actually, because in fact, shapes in ray marching are so simple that they're just one number.
And what is really fun though also is that this value, I put it in tag, I can do a uniform value with that, which might be controlled by a keyboard.
That's right.
Or by a mixtape.
Yeah, or a MIDI
or
controller.
by a lip motion.
Yeah, or a fader or
Everything
whatever.
you can. And that's also why I think shader coding is really powerful. That's because everything is a number, everything is a mathematical function, and everything is a variable. So everything can be plugged to whatever controller you want. I'm sorry, but when you understand a little bit what is going on there. You don't need to understand everything, and I share your advice. Of course, you don't need to understand anything, but the more you want to do with it, the more you need to understand what you are doing.
Absolutely right.
But it's not that mathematically complicated. I think if you passed by a website course on the the level of high school level in mathematics, that's all you need. Matrix a little bit, maybe it's above high school, but it's this. Apart from that, it's dot product, cross product, and it's something you can see in a high school teaching. So
high school math is, not that hard. You know what I mean? I would argue even lower, even than that. I don't know. I mean, I don't. Okay, I kind of do now understand what a dot product is, but trust me, man, for like a couple of years, I was doing pretty cool stuff in ray marching, not understanding actually even what a dot product is. And so when you want to reach that next level, Flopin's point totally makes sense. The more you understand about it, the more you can do advanced stuff. But that doesn't mean you can't do cool stuff.
No, you can do cool stuff without understanding. But if you are understanding things afterwards,
it helps.
You can do whatever you have in mind.
Yeah, that's right.
Because you're tweaking number, and if you understand what is the number you tweaking at this place, how to tweak it, what this function do to tweak it, you can do anything you have in mind. Really anything. And I encouraged you to start as Eviviville said, and that's why we will going to give you some links.
Yes.
But my second advice will be, if you want to keep it and to continue on this path and want to do more complex stuff, or just doing what you have exactly in mind, try to understand more the mathematics behind it. It's not, don't be afraid, it's not that difficult. And maybe you should find someone who can help you with that, or some of the links we will provide are really great at explaining a little bit of mathematics behind, for example, Voronoi or stuff like that. Maybe it's time for question.
Do that.
Do we have time for question? Maybe.
Yeah. Oh, you guys. Yeah, please. Questions.
Or if you want to see something else that can be displayed in 1 minute, maybe.
Shall we show them the? No, we can do the links in a minute. Do you have anything to show? Why don't you show them one of your shaders?
One of my shaders.
From Shader Toy or something.
Okay, if you want.
I don't know, or like from Bonzo. Or,
yeah.
Or if you want to show them something better, you could show them one of my shaders.
Do you want to see your shader?
I was joking.
I'm sorry, you can see I'm a big fan of Ori and the Blind Fairy that cooks so delicious.
Just show some of your stuff, bro. It's your computer as well. You're driving this workshop. Show them.
So Shader Toy.
Loads of stuff on Shader Toy.
So Shader Toy is a great. I will argue that Shader Toy is not really a great start, because people usually don't comment their code, and it might be a little bit obscure.
Shane does. Shane has really great.
Shane, apart from Shane.
Before you go to Excite, read through Shane's.
Shane, yeah. Shane. If you're watching Shane, I fucking love you, bro.
So in Shader Toy, the ones who really explain things in his shader is Shane, like that.
Shane is a legend. I love you, broski. I've stolen so much code from you. And he just commented on one of my shaders last week, and it just made my day. He was saying, "Oh, I
And,
love this shader. It looks so amazing." I was like, "Oh,
what he do
Shane."
is pretty awesome, and he comments everything.
Yeah, although to be honest, I'm gonna be the non-math genius in the house. But some of the stuff, although Shane explains very well,
Yeah.
it's still some of it is quite advanced. Like
Yeah.
Shane stuff is quite advanced, basically.
But you have all this comment here that he
But
explaining things.
he's brilliant at commenting his code, and it's invaluable stuff right there. So Shane on Shader Toy is a really good account.
Yeah. Also, maybe something simpler.
Do you know what? Actually, I
is-
insist. Put one of my shaders because I also comment every single line of my shader.
Okay.
And while I'm here, why not? Unless you want to show yours.
No.
I have very abrasive sort of style of commenting my code. I like to make jokes about your ex-girlfriends and stuff like that.
How many V have you in your name?
Yeah, well, yeah, it's 4.
Oh,
Come on, man. Not that hard.
you're such.
Still 9.
Nah, still nothing. See. Okay, c'est bon.
Oh, look at those.
They are so heavy, like you.
Oh my god. Is this?
I'm not on the NVIDIA GPU. That's why.
Oh well.
It's because it's a laptop, Optimus, some there. While it's loading,
Yeah.
I will just show you the
Please
book
do
of
put-
shader, for example.
Oh, that's a
for
really
example.
good point. Yeah, but that's a bit. Well, still, it's really a very good point actually. Book of Shader.
The book of shaders,
It's a
which
bit
is
more broad than just what we do in ray marching. It touches on
Yeah,
every single types of shaders, whereas when we do ray marching, we only do pixel shading essentially.
Yeah.
But it's really well done, really well written, and a
And
great
it's-
entry for shader.
It's translated in many languages by or just or people who are benevolent
Volunteers.
volunteers. So you have English, French, Spanish, etc. You have a lot of things that are covered.
It's really well written as well for like banging an
Yes.
entry and stuff.
For
It's a
example, the pass on the cellular noise might be something you can recognize. It's Voronoi, the cellular noise like that. Okay. And you have a lot of things to learn from that. Syntopia is pretty well too, I think. Syntopia. No, not like that. Not that. It's not Syntopia.
I don't know this website.
You don't know?
No. Enlighten me.
Syntopia? No. Oh, shoot. Well, I have a shadow coding stuff like that. I would also recommend this one, Hello World. Maybe I can send some people. It's quick exercise about...
That's super interesting for beginners, guys.
and you have, for example, here, the exercise wants you to displace a green circle, a green stuff, instead of red. And
That's
all you have to
interesting.
do is change the GL color here from red to green. Uh-oh, I'm here. It's meant to be simple, but I can't type things. Why that? Sorry. Yes. So I can type green here. Your answer. He's checking the answer. I got it. Nice work. I can go through the other exercise, etc., etc. And
That's super cool.
it's getting harder and harder. And at the end, you even have the polar coordinate modulo function,
Wow.
and you can learn it.
Yeah, it looks
right
like the Mercury stuff as well that they did.
So that's kind of cool. The book of shaders is cool also.
Show them
since-
the ray marching
Yep.
page by. Oh, look at that. Oh man, these shaders are beautiful. I wonder who made those. Me.
And we need to stop. So, sorry.
Okay, just show them quickly the ray marching IQ page. Sorry. Because this was mine and it's bullshit. But sorry, this is what I was gonna say. The page that has all the functions is just Google. You don't even have to put IQ.
What?
What? No, that's the Mercury. That's a
That's
bit more
Mercury.
advanced. But very good point, by the way, mate. But no, it's this page I was looking for. Now, all I'm saying is, if you want to get this page, actually, I've done it so many times. Go on Google and type ray marching modeling. It's the first result.
Yeah.
This page has every single primitive function you can. Well, not
Dream
every
of.
single, because there's more actually. But anyway, this has loads and loads of content for ray marching, copy and paste stuff. So the sphere function we used is right there. You see? Same. You want a box? It's there. You want a round box? It's there. So literally, that's all I did when I started ray marching. Go on this page, copy this function, paste it in Shader Toy, and that's how you get your thing. There's also more, just finally,
no.
there's also more functions about blending shapes together. You know how we did the operations to add shapes together? It's all in there, bros. That's it. That's your ray marching reference right there.
Okay, so we need to stop. If you
We're
have
done.
questions, you still can discuss with
Come
us.
to
during
us,
the-
talk to us. But we're done. Thanks to the
thank
Orga
you.
team. Thanks a lot, bros. Cheers.
Thank you.
Thanks, Floppy.